Hi there, everybody. We're going to take a look at proving something about GCDs and using the Euclidean algorithm, and find that this can be kind of a powerful thing to do. Um, we'll see that it kind of helps us in terms of being able to manipulate some equations to prove things that before we had to kind of do a little bit more hand wavy type stuff, legitimate, but this is going to be a little bit more straightforward. So the one I'm going to look at is let A, B, K be positive integers. And we want to prove that the GCD of Ka and Kb is equal to K times the GCD of A and B. And so we could just like do a bunch of examples, and certainly that would be one way of looking at it. But instead, well, let's start with that. So let's kind of say some easy thing. First of all, would be let's let G equal the GCD of A and B. Okay. From that, I can claim, not claim, that KG, KG rather, divides Ka, and Kg divides Kb. Which, I mean, if you think about it, that should make sense, because we know that G goes into A, and all I'm doing is multiplying both of those values by some common factor. So like, for instance, if I knew that 2 divides 6, and then I multiplied both of those by 3, then I know 6 divides 18. So should make sense. But based on the fact that I know Kg divides Ka and Kg divides Kb, at the very least, I know that Kg has to be less than or equal to the greatest common divisor of Ka and Kb. We know it's a divisor, clearly, because it goes into both Ka and Kb, but we haven't yet shown that it's got to be the greatest common divisor. And so the question we have to ask is, how do we know? Can't seem to spell. That we don't accidentally have that the GCD of Ka, Kb is actually greater than. So it's a strictly greater than rather than greater than or equal to than Kg, which, remember, we said is K times the GCD of AB. So in other words, how do we know for certain that our Kg isn't actually, it's not at all the greatest common divisor, it's just a divisor. And here we're trying to, we have to worry about all these inequalities. So instead, let's take a look at how to use the Euclidean algorithm, because it's kind of difficult to prove otherwise, but with the Euclidean algorithm, it actually goes pretty straightforward. So I'm going to just shift and move this up a little bit so I have some space. And let's change up some colors. Let's go to green. Okay, so we're going to use the Euclidean algorithm. So what this means then is I'm going to look at A and B. Okay, and so I'm going to say I want to divide A by B. So using the division algorithm, we know that A is going to equal Q sub 1 times B plus R sub 1. So there's some quotient out there and some remainder. Okay, pretty straightforward. And then I can continue that. Here's the Euclidean algorithm piece comes in. So now I'm going to pull over and I'm going to say, okay, then that means B, I can divide B by R sub 1, and I get Q sub 2, and then I have a new remainder, R sub 2. And I can continue that. And then I move R1 over, and now I have a third quotient, dividing R1 by R2, and I get R3. Okay. And this, we can keep going until eventually we get to R n minus 2 equals Q n R n minus 1 plus Rn. So if you notice the different subscripts here, so like for instance, I have a 3 here and a 3 here, so R sub n and R sub n, or Q sub n. This one, the 2 is 1 less than that, so I have my n minus 1. This is 2 less, so n minus 2. So that's kind of how that works. How do I know that I'm done? Well, assuming that I've kind of gone through all of these pieces, then I know that at this point, then the next one is I'm going to go Rn minus 1 equals Q n plus 1 R sub n plus 0. Okay, so I know, so basically what this is telling me then is that the GCD of AB is R sub n. So we could just also use just K times, or G equals rather R sub n. Because remember we originally defined G as the GCD before. Okay, make sense? Just following it through, we know that using the Euclidean algorithm, we have greatest common divisor. So here's where things get kind of interesting, because I want to be able to show, like I want to be able to look at the relationship of Ka and Kb. So why don't I just go ahead and divide Ka by Kb? Well, if you look at the equations here, here's where the kind of the power of Euclidean algorithm comes in. We got a bunch of equations. We've got tools that we learned how to use equations on a long time ago. So I'm going to take my value k, and I'm just going to multiply everything in that first equation by k. So now I have Ka equals Q1 Kb plus Kr sub 1. I can multiply everything by k. That works. And I'm going to do the same thing to the next term. So now I have my Kb. Here's my Kr1 and Kr2. So you'll notice that now, following the Euclidean algorithm, my Kb here is now at this point. My Kr1 is now at this point. So we're just going to continue that all the way through. And so then I get K here. And notice where I'm putting the K. The Q's are kind of a throwaway in this one. Q's, the quotients matter later on, but for this particular problem, it's kind of a throwaway. I'm more interested in all those remainders as I continue down. And I keep multiplying it down. Every equation, I multiply everything by k until I get to this. And you'll notice that what this essentially means then is that k sub n, I'm sorry, k times r sub n is the GCD of Ka, Kb. And the reason we know this is because now that's what we started with up here. We were dividing Ka by Kb and using the Euclidean algorithm. And so for the same reason why in the original one, the GCD was R sub n, now it's K times R sub n. But notice what R sub n is. R sub n, so this is, I'm going to put the K times R sub n on this side, which is just K times G, because that's what we said R sub n equaled. And then, based on what we did up here, that means this is K times GCD of AB. And so, this is what we were trying to show, is that the GCD of Ka, Kb is equal to K times the greatest common divisor of A and B. So, we're just using equations, and that's the nice part about this. Is we can use all the tools we have learned previously about solving equations, and it works pretty well. So this is just one example of using Euclidean algorithm for things like proofs about greatest common divisors. The definition of a greatest common divisor is a much more difficult way of proving this exact same thing, but the Euclidean algorithm really helps us out. So that's it for that one, and hopefully that helped you understand that a little better.